Good morning. Here we are going to use Millman theorem to solve an unbalanced three-phase system. As I said, here we have three voltage generators in parallel, and Millman theorem is something that we use to transform many voltage generators that are connected in parallel to a single one. This circuit we can transform it to a single voltage generator. Here we will call this one V0 and here Z0. So these three generators we will try to transform them to a single one. How do we do it? First of all, we transform every generator to a voltage generator to a current generator. So the first one will be, we can transform it to this one. Here we have V over Z1, the current generator. Here we have Z1. To second generator we can transform it to this one. Millman theorem is a mixture of Norton and Thevenin theorem. Okay, so we transformed all the voltage generators to current generators. Here we have V3 over Z3, Z3. Okay, so it means we can say that these three current generators, we can transform them to a single current generator, where here we have V1 over Z1 plus V2 over Z2 plus V3 over Z3. This is the current that we have replaced, and here we have 1 over Z1 plus 1 over Z2 plus 1 over Z3, which is equal to 1, which is equal to 1 over Z0, and this we can call it I0. So now we can go back to transform this current generator to a voltage generator that will give us a V0, which is equal, V0 is equal to V1 over Z1 plus V2 over Z2 plus V3 over Z3 over 1 over Z1 plus 1 over Z2 plus 1 over Z3. This is V0, and Z0, 1 over Z0 will be equal to 1 over Z1 plus 1 over Z2 plus 1 over Z3. Okay, let's now take our unbalanced system and try to solve it. Suppose that Z1 is equal to 8 plus J6, Z2 is equal to 6 minus J8, and Z3 is equal to 3 plus J4. So it means in polar form we have 10 and 36.87 degrees in ohms. Here we have 10 minus 53, 13 degrees, and here we have 5 and 53.13 degrees. And the admittance Y1 is equal to over z1, it means we have 0.1 and minus 36.87 Siemens. y2 is equal to 0.1 and plus 53.13 degrees, and y3 is equal to 0.2 minus 53.13 Siemens. Now we can calculate V0. V0 is equal to V1 times Y1. So it means here it's a three-phase system. This is 220 0 degrees volt. Here V2 200 minus 120 degrees volts, and V3 is 220 and minus 240 degrees in volts. So here we have 220 0 degrees times y1 times 0.1 and minus 36.87 plus V2, which is 220 minus 120 degrees times 0.1 minus 50 plus 53.13 plus 220 minus 240 times right here 0.2 minus 53.13 divided by y1, which is equal to y1 is equal to, here we can write y1 is equal to 0.08 minus, in algebraic form, 0.06. y2 is equal to 0.06 plus j 0.08, and y3 is equal to 0.12 minus j 0.16. So it means here we have the sum of the three, 0.26 plus minus j 0.14. The result here, so 22 times cosine minus 17.6, 220 times 22 times sine minus 36 will give us minus 13.2 j. Here is 22 and argument will be minus 66.87. 22 times cosine minus 66.87 will give us 8.642, and sine minus 66 times 22 will give us j 20.23 plus the argument here will be minus 293, which means it's 66.87 times 44, so will give us 17.284, and sine 66.87 times 44 will give us plus j 40.46 divided by 0.26 minus j 0.14. This will give us 43.526 plus j 7.03 over 0.26 minus j 0.14. Here we'll have in polar form 44.09, argument 9.18 degrees over 0.29 5, argument minus 28.3. This will give us 149 in volts, 0.3, and argument 37.47 degrees in volt. In algebraic form, it's 118.5 plus j 90.83. So V0 is equal to 149.3 and 37.47. And now we're going to calculate the currents using this voltage V0 that we just calculated. Okay, now to calculate I1, we have to, if we call this 0, A, so it means that I1 will be equal to V1 minus VA0, which is equal to V0 divided by Z1, so it means it's 220 minus 118, this is VA0, 0.5 minus J 90.83 over Z1, which is equal to 1036.87. I1 will be equal to here we have 101.5 minus J 90.83 over 1036.87. So this is in polar form 136.207, argument minus 41.82 divided by 10 and 36.87 will give us a current of 13.62, argument minus 78.69 degrees in amps. In algebraic form, 2.671 minus J 13.356 in amps. Now we can go and calculate I2. I2 is V2 minus VA0 over Z2, and it will be equal to minus 110 minus J 190 this is V2 0.52 minus 118.5, which is VA0, and minus J 90.83 over 10 and minus 53.13. So it will give us a voltage of minus 228.5 minus J 281.35 over 10 minus 53.13 in polar form. Here we have 3 362.45 and argument minus 129.08 over 10 minus 53.13 give us current of 36.24 minus 75.95. This is minus 129 plus 53, and in algebraic form we have 8.8 minus J 35.16 amps. We have now to calculate I3. I will calculate it here. I3 will be equal to V3 minus VA0 over Z3. I will give you the result. It's 110 minus 110 plus J 190 minus 118.5 minus J 90.83 over Z3 which is equal 5 and argument 53.13. We have here minus 220.5 plus J 99.17 over 5 argument 53.13, and here we will have in polar form 249.1 argument plus 156.54. We are in this quadrant, so we divide it by 553.13, so it means we have a current of 49.8 and argument 156 minus this will give us plus 105.41 in amps, so it's minus 11 in algebraic form, 55 plus J 48.46, and here we can verify that I1 plus I2 plus I3 should be equal to 0, so I1 here plus I2 plus I3 should be 0. And that's it. And thanks very much for your attention.